Hello everyone, welcome again to another lesson from the chapter The Solid State. In this video, we shall discuss about the calculation of the spaces occupied, that is the packing efficiency of the solids. Now in the previous lessons, we have seen that in any type of packing, some voids or empty spaces are always present. The percentage of the total space filled by the particles is called packing efficiency. Let us first calculate the packing efficiency in a simple cubic unit cell. Now let us suppose the edge length of the unit cell is A and the radius of each sphere is R. As the spheres are touching each other, evidently the edge length A is twice the radius R. Now, the volume of any sphere, as we know, is given by the formula 4 by 3 pi r cubed. We have already seen that the number of spheres per unit cell of a cubic lattice is 1. Also, we already know that the volume of any cube is given by A cubed. Thus, by substituting the value of A, the volume of the cubic unit cell is given by 8r cubed. Thus, by putting these relations for the volumes of the sphere and the unit cell in the formula for packing efficiency, we can calculate the packing efficiency for a simple cubic unit cell, which is 52.4%. Now let us calculate the packing efficiency of a face-centered cubic unit cell. As the sphere on the face is touching the spheres in the corners, here we can see that the face diagonal AC is equal to 4 times the radius R. Also, if we join the centers of the spheres, we see that it forms a right angled triangle ABC, which is right angle at P. Thus, by applying Pythagoras theorem, we see that AC is equal to root 2 into A. Equating the values of AC, we can get the relation between the edge length A and the radius R of the spheres. Now, using this relation for the edge length A, we now know the volume of the unit cell. Keep in mind that here, we have not yet considered the volume of the spheres, and this is just the volume of the empty unit cell. To find the total volume occupied by the spheres in the unit cell, we need to firstly know the number of spheres per unit cell, which is also known as the rank of the unit cell. Now, for a face-centered cubic unit cell, the number of spheres per unit cell, or the rank of the unit cell, is 4. Thus, the volume of the 4 spheres is equal to 16 by 3 pi r cubed. Thus, by putting these relations for the volumes of the spheres and the unit cell in the formula for packing efficiency, we can calculate the packing efficiency for a face-centered cubic unit cell, which is 74%. Now finally, let us calculate the packing efficiency of a body-centered cubic unit cell. Now, as the sphere at the body center touches the spheres at the corners, the body diagonal AD is equal to 4 times the radius R. Now, if we consider the right angle triangle ABC, the value of the face diagonal AC can be calculated using Pythagoras theorem. This value can then be used to calculate the value of the body diagonal AD in terms of edge length A by applying Pythagoras theorem in the right angle triangle ABC. Then, by equating the two values of AD, we can get the relation between the edge length A and the radius R of the spheres. Now, using this relation for the edge length A, we can now know the volume of the unit cell. Again, keep in mind that here we have not yet considered the volume of the spheres, and this is just the volume of the empty unit cell. Again, to find the total volume occupied by the spheres in the cell, we need to first know the number of spheres per unit cell, or the rank of the unit cell. For a body-centered cubic unit cell, the rank of the unit cell is 2. Thus, the volume of the two spheres is equal to 8 by 3 pi r cubed. Thus, by putting these relations for the volumes of the spheres and the unit cell in the formula for packing efficiency, we can calculate the packing efficiency for a body-centered cubic unit cell, which is 68%. To complete our discussion of this lesson, let us discuss about the relationship between the nearest neighbor distance d, edge of the unit cell A, and radius of the atom r for pure elements. For simple cubic unit cell, the distance between the nearest neighbor distance d is AB, which is equal to the edge length A. Also, for pure elements, the radius r is d by 2, since the atoms of the spheres are touching each other. For a face-centered cubic unit cell, the distance between the nearest neighbor distance d is equal to half of AC, but the length of AC, as seen earlier, is root 2 into A. Thus, d is equal to A by root 2. Also, since the radius r is half of d, then radius r is equal to A by 2 into root 2. For a body-centered cubic unit cell, the distance between the nearest neighbor distance d is equal to half of the body diagonal AD. But the length of AD, as we have derived earlier, is root 3 into A. Thus, d is equal to root 3 into A. Also, since the radius is half of d, then the radius r is equal to root 3 into A by 4.